Okay, so now our next section's on rates of change, which of course is what calculus is all about. Because remember, a derivative measures a rate of change of something. One quantity changing with respect to another quantity. And 9 times out of 10, that's going to be time in a lot of things we look at. Steeper the curve then, the faster the quantity changes. Because it means its derivative, which remember measures the slope of the tangent, or the slope of the curve if you like. So the tangent, the steeper the tangent, then the faster the change. So here's a graph, just a random graph. There's point P. So at point P, that slope's positive, so we know the derivative is going to be positive there. We know the curve's increasing, but by using calculus, it means we don't actually have to draw the graph. We just find the derivative, and if it's positive, we know that had we have drawn the graph, then that tangent would have been a positive slope. Then, of course, something like this one, Q, was our stationary points. So function x is stationary. And then over there at R, that'll be where we know the quantity is decreasing. If I have 2 points on our curve, so PQ, the slope of that secant would give the average rate of change. Now, average rate of change is not that useful. We're more interested in instantaneous. And so that would be the actual tangent itself, so the derivative. So if we want to find average rate of change, then, okay, it's like saying what's the slope of the line that joins these 2 points? Whereas if it's instantaneous rate of change, okay, what's the value of the derivative at that point? Which brings us to travel graphs. Travel graphs, of course, are something you've been seeing now for a long time. In fact, the example I'm about to put up comes from a wonderful Year 9 textbook. So here's a typical sort of travel graph we would have seen back in Year 9. A coach leaving a depot, and there's the wonderful graph that we have. But of course our travel graphs back then tended to be nice straight lines, and they asked questions like, oh, how long was the first stop? Well, of course what you were doing, although you didn't realise it at the time, you're saying, oh, well, when is the tangent horizontal? So, but back in Year 9 you would have said, oh, when's it flat? That must have been when it stopped. But essentially that's what you were doing. Now the first time it was 30 minutes. When did the coach start to return to the depot? Well, that was like saying, well, when's the rate of change going negative? Because we're going back in the other direction. So there it is, at 1:30, our curve is going back down. How fast was the coach travelling on that return trip? Well, we would want to find the slope of the tangent. Fortunately, it's a straight line. So with speed equals distance over time, of course, 100 kilometres per hour. And calculate the average speed for the whole trip. Well, we travelled 400 kilometres over 6.5 hours, so 61.5 kilometres per hour. So they're the sorts of things that we asked. Now, thanks to our calculus, there's no reason why those curves have to be straight. And so here's one. We're bouncing a ball, and its distance from the ground is graphed. It turns out to be a nice parabola, so we can actually get an equation for that graph, and that could be useful too. So distance, remember, is the total amount travelled, as opposed to displacement, which is just, well, how far are you from that starting point or that reference point that you're talking about? So find the height of the ball after 1 second. Well, we can read off our graph, but we've got an equation, so I can sub in, and there it is, 35 metres above the ground. At what other time is the ball this same height above the ground? Well, we want to know when x is 35. We solve our little quadratic, and we end up with 1 or 7. So it must be after 7, because 1 was when it was going up, 7 is when it was going down. So average velocity will be the change in displacement over time. That's what I was saying before. Remember, if we were finding average, there's the formula. If it's change in displacement over change in time, it is indeed the slope formula. So what is the average velocity during the first second? So subbing those values, we get 35 metres per second. What about during the 5th second? Now you've got to be careful. The 5th second starts at t equals 4. Right? Because if you think about it, the first second starts when t equals 0. So when t equals 4, it's at 80. When t equals 5, it's at 75. So we'll plug that into our slope formula. -5, we're talking about velocity, not speed, so the negative is important. So the negative tells us we're actually going back in the well, back to the ground. Find the average velocity. The average velocity then, it's 0. That's the weird thing about average velocity. I mean, it can be 0, which sort of sounds strange, because it's like saying, well, on average, it just didn't move. And of course it did, but it's back where it started from. Average speed then is distance travelled over time. So the average speed during the 8 seconds is distance travelled over time. So it's actually 20 metres per second on average.